Theorem again on the linear transformations. Let T is a mapping from U to V be a linear map. Then if T is 1 1 and U1 U2 up to UN are Li, okay, vectors in U, then T of U1, T of U1, T of U2, T of UN are also Li. So Li to Li, okay, you need to have Li vectors in U. Then this Li vectors in V, of course. Images, okay, right side. U vector space, V vector space, T is a mapping. So U1 here, the T of U1 will be here. U2 here, T of U2 will be in the V. Okay. So you are Li vectors in the U, then T of U1 U2 will be Li vectors in the V images. Okay. So only verify Li vectors. So let T is a mapping from U to V be a linear mapping. Linear. Also, this T is given to you 1 1. You know 1 1. Okay. Definition. And also these vectors U1, U2, UN are Li vectors. Li. Okay. Its multiple will be 0. Alpha 1 0, alpha 2 0, alpha 3 0. Okay. Every scalars multiples of that vectors must be, okay, 0 vectors. And now I will show this T of U1, T of U2 will be Li. Okay. So Li or LD, you know method consideration. Okay. Consider alpha times scalar times alpha 1 into T of U1, alpha 2 into T of U2, and so on. Alpha n into T of Un equal to 0. Sum will be 0. Scalar multiple sum, okay, will be 0. That will be 0. And then finally show alpha 1 0, alpha 2 0, alpha 3 0, alpha n 0. Each scalar 0. Okay, each scalar 0. Then we can say it is a Li vectors. Okay, at least one of the vectors will be not 0. Then confirm that it is a LD. Okay. Now T is a linear as given to you. Is a linear. Okay. Therefore alpha inside T of alpha 1 U1, T of alpha 2 U2. In this way, T of alpha n inside and 0. And also we know by one theorem is T of 0 is 0. T of 0 is 0 by theorem, previous theorem. Again now addition law. So T of total. So T of alpha 1 U1 plus alpha 2 U2 up to alpha n Un will be 0. T of 0. Reason here linear is a linear transformation. Therefore this is. So T of this equals to T of this, and it is now 1 1. It is now 1 1. Therefore what? Okay. T of U equals to T of V, then U equals to V. Therefore alpha 1 U1 plus alpha 2 U2 plus alpha n Un will be 0 by 1 1 is a 1 1. Okay. So sum will be 0. But Li vectors given to you. Okay. U1 to U2 UNs are Li vectors. Li means each multiple 0. Each scalar multiple of that vector will be 0. So each multiple 0 here. So alpha 1 will be 0, alpha 2 will be 0. In this way, alpha n will be 0. So it's 0. So So we assume consideration scalar multiple of the vectors which you have to show is Li, and finally we show all are 0, alpha 1 0, alpha 2 0, alpha n 0. That is what? That vectors must be Li. So vectors are T of u1, T of u2, T of un, okay, are Li. Vectors in where V. Okay, so if u1 u2 are Li, then T of u1 is also Li. But condition is 1 1. Okay, that mapping must be 1 1. Okay, so T is 1 1 means T of u equals to T of V, then u equals to V. That is the condition of 1 1. Okay, T is 1 1. T of u equals to T of V, then u equals to V. Here we use technique. This example, prove that a linear map T from V3 to V3 to V3 defined by this like. So T of E1 is E1 minus E2. T of E2 is 2E2 plus E3, and T of E3 is E1 plus E2 plus E3. E1 plus E2 plus E3 addition of 3. Now is neither 1 1 nor on 2. Okay, not 1 1 and not on 2, both. Okay, neither 1 1 and neither on 2, both. So when 1 1, just previous theorem. Okay, nt equal to 0. Okay, nt null space equals to 0, and on 2. Okay, RT range. Okay, is completely equals to V right side. See. So let T is linear and linear map T from this is defined by in this way. Now E1, E2, E3 you know. Okay, so let E1 means 1 0 0 standard basis, E2 means 0 1 0, and E3 means 0 0 1 are standard basis of V3. U T from V3. These are standard basis of V3 left side. Okay, into main space. Therefore, now here T of E1 means E1 minus E2, 1 0 0 minus 0 1 0 will be 1 minus 0 0 0 minus 1 minus 1 0 1 0. T of E2 will be okay 2E2 plus E3, 2E2 plus E3. So 2E2 plus E3 0 0 1. So 2E2, sorry. So 2 into 0 plus 0 0. 2 into 2 plus 0 2. 2 into 0 plus 1 is like 0 2 1. T of E3 will be E1 plus E2 plus E3. Addition of all the three will be what? 1 1 1. Okay, add all three. These are given to you. T of E1. Okay, now comes to solution. So first onto. Onto means range. Okay. Onto depend on the range. So RT. RT we know by previous theorem. What is RT? Set of images. Okay. T of E1 T of E2 and T of E3. Okay, span of T of by theorem U1, U2, U3's okay span of this one is a range by the theorem. Now here T of E1, this vector 1, -1, 0. Second is 0, 2, 1, and third is 1, 1, 1. Okay, so this will be range RT. But Li must be, okay? Remember, span must contain Li vector anyhow. Okay, so this check first of all LD or Li. Now we check matrix method to LD Li. 1, -1, 0. Determine okay equal to 0 LD and not equal to 0 Li. Okay, so the short technique, determinant technique. Okay, so 1 into 2 into 1 2 minus 1 into 1 1 minus and minus plus 1 0 into 1 0 1 minus 1 1 and third is 0 into is all zeros. So 2 minus 1 1 into 1 1 0 minus 1 minus 1 into 1 minus 1 0. So determinant will be 0 then LD. Okay, determinant of these three vectors is 0 is what? These vectors are LD. Okay, so therefore remove the vectors. Above vectors are LD. Therefore remove the one. So remove one vector. Say last, always remove last vector. It's now remaining only 2 RT. So span of only now these two vectors. And the two vectors are of course okay. So this now your range. Therefore dimension number of vectors 1 and 2 vectors are in this. Okay, dimension RT is 2 and which is not matched with dimension of right side V3 3. Okay, so RT must match must be this one. Okay, therefore RT cannot be equals to V3. I want RT must be equals to V3. Okay, go to line then 1 2. So this is not possible. Therefore T is not 1 2. Okay, so neither 1 1 and 1. So first we will show this is 1 2. Now 1 1. So 1 1 depend on the NT against previous theorem. NT. Okay, T mapping from V3 to V3. NT here 3-dimensional vector. Suppose say XYZ is a vector of V3 such that condition by definition is T of XYZ equal to 0. By definition of NT, vectors of U left side domain space such that T of this equals to 0. So we solve separately. So T of XYZ equals to 0. But your T is given to in terms of E1, E2, E3. So this convert to E1, E2, E3. So this is written as okay E1 into X, E2 into Y, E3 into Z equals to 0. Standard basis, that's why. Now linear, therefore X outside T of E1, Y outside T of E2, Z outside T of E3 equals to 0. So X out. So T of E1 is we know 1 minus 1 0. Y outside. T of E2 we know 0 2 1. T of E3 we know 1 1 1. Now solve. Equation X plus 0 plus Z equals to 0. Second, minus X plus 2Y plus Z equals to 0. And third, 0 plus Y plus Z equals to 0. So we have the three equations. So solutions. So from this x equals to minus z, and from this y equals to also minus z. So in terms of z, already LD. Therefore this cannot be solved equations. This equation can be solved because LD vectors are. Li vector, then this can be solved. So this in terms of x in terms of z, y in terms of z, and z itself. So therefore your NT will be x, y, z. Okay, so x is minus z, y is minus z, and z is z itself. Or this is same as minus z is common. 1, 1, minus 1, set minus z common. Means what? It is now span. Multiple. Some multiple means what? Span up. So span up this single vector. Span up a single vector. So NT equal to this. So NT contains one single vector. That means what? This NT not 0. NT is not 0. NT equal to 0 vectors, then Li. Yes, please. NT contains 0 vectors, then it is a Li. So contains 1 vectors. Okay. Therefore, this also not 1 1. So 3 is not 1 1. Okay. So it is neither 1 1 and neither 1 2 also. So this example. Now main theorem on this, also called as a rank nullity theorem. Okay, rank nullity theorem. So statement: let T is a mapping from U to V be a linear map and U is a finite dimensional vector space. Then by this theorem, what? Dimension of RT, okay, range space, plus dimension of NT, this must be equals to dimension of U, okay, left side, domain space. Dimension of RT means what? You know, rank. Dimension of NT means what? Nullity. This must be equals to dimension of U. So this is called as a rank nullity theorem. Okay, rank plus nullity. Okay, 2 plus 1 must be 3. Very must be understood. So rank plus nullity must be equal to dimension of U. Okay, domain space. Okay, so remember this MCQ can be asked on this. So now take proofs, because B proofs. The examples on this small examples. Let T is a mapping from V2 to V3 defined by linear map, defined by in this way. So T of x1 x2 equals to x1 minus x2, x2 minus x1, and minus x1 is like defined by. Show, question is show that this T is 1 1, means NT equal to 0. When T is 1 1, NT must be equal to 0. Vectors is NT must be equal to 0 for the theorem. So going from V2 to V3 be a linear map defined by in this manner. and show T is 1 1. So 1 1 depend on the NT. So take NT by definition. So we have NT vectors of U, V2 space, 2-dimensional space. So x1, x2, 2-dimensional vectors of this V2 space, such that condition T of this must be equals to 0 by definition. Vectors of U such that T of U equals to 0. So U, V2 space, okay, domain space, V3 codomain space. So take separately. Let T of x1, x2 equals to 0 as solve. So T of given to you in terms of x's, no problem. So x1 minus x2, comma x2 minus x1, comma minus x1 will be 0. 0 means what? 0 vector. I want here 3 dimensional. So 3 dimensional 0 vectors. So respective will be 0. So x1 minus x2 will be 0. x2 minus x1 will be 0. Minus x1 will be 0. Okay. So from this easily we get x1 will be 0. And put here, from this here, x2 will be 0. Okay. So x1 will be 0. So as of here, NT, 2 vectors are there. x1 is 0, x2 is 0. So 0. So NT, okay, as 0, 0 vector. This is 0 vector. So NT equal to 0, that means 1 1. So NT is 1 1. So NT is 0, then T is 1 1. Theorem. So theorem on the Range theorem. If U and V are finite dimensional vector spaces over the same field of same dimension. Then
चालन ने क्यों स्टार्ट किया?
हाँ?
नवीन कौन स्टार्ट किया?
मैंने स्टार्ट किया हूँ। कितना?
12-23.
बता 5 मिनट से होता। Then a linear map T from U to V is 1 1 if and only if T is onto 1 1 then onto. Simple. So U and V are the two vector spaces of over the same field. Here suppose of same dimension. Okay, dimension is same. Then remember T is 1 1 if and only 1 2. Okay, so as dimension of U equals to dimension of V, same dimension. Now given that T is 1 1. So when 1 1, just we know by theorem, NT equal to 0. Okay, NT equals to 0. So NT 0 is what? Dimension of NT will be 0. NT contains 0 vector. 0 is 0. So dimension of NT will be 0. So dimension of NT will be 0. Then by rank nullity theorem, we have rank plus nullity equals to dimension of U by the theorem. So this rank nullity 0 equals to dimension of U. So rank means what? Dimension of RT. Dimension of U. Dimension of V. Dimension of U equals to dimension of V. So dimension of RT equals dimension of V. That means what? RT equals to V. RT range space covered entire space V. RT will be covered entire space V means what? Onto. You know onto. Okay. Alright side. Range space is entirely V. Then onto. So T is 1 1 then T is onto. But when? So only verify only one condition 1 1 and then obviously onto. When dimension of U equal dimension of V then same. Okay. Dimension of U's vector space and dimension of vector space are same. V3 to V3, V2 to V2. Okay. So same dimension then only verify 1 1. Obviously becomes onto. Okay.